Hi, I'm Ashley, and we're reviewing Chapter 17, The Fundamentals of Spectrophotometry. So, what is spectrophotometry? Well, it is any technique that uses light to measure chemical concentrations. So, what is light? Light comes in two forms. It has a waveform and a particle form. So, the waveform has a wavelength, which is the distance between crest and crest, or trough and trough, represented by lambda. And then it also has a frequency, represented V, which is the number of complete oscillations that a wave makes in 1 second. So this is represented by hertz, and it is 1 over a second. And when you compare these and put them in a relationship together, you get C equals V lambda, which C is the speed of light in a vacuum, which is 2.998 times 10 to the 8th meters per second. And then for a particle, a photon, or a particle, carries an amount of energy. So that relationship is represented by E equals HV, which is Planck's constant, which is H, and that is 6.626 times 10 to the negative 34 joules times seconds, and V, like I said earlier, is frequency. So when you combine these two formulas, you get a new relationship, which is energy equals Planck's constant times the speed of light divided by wavelength, which equals this. And this right here is simply a wave number, which is 1 over the wavelength. And what this tells us is that energy is inversely proportional to the wavelength and directly proportional to the wave number. So when light has a longer wavelength, there's less energy, and when light has a shorter wavelength, there is more energy. And this can all be observed on an electromagnetic spectrum because it shows all the ranges of wavelengths and frequencies of electromagnetic radiation, and we, as humans, can only see a very small part of that, of the visible light. So now that we understand what light is, what happens when a molecule absorbs a photon? So, energy increases and the molecule becomes excited. What I mean by that is here's the ground state and here's excited orbitals. When energy comes in, an electron is excited and sent up to a higher energy orbital. And then that energy, or that electron, can go down to lower orbitals in the excited state. But eventually, it has to come down to the ground state because it's more stable in the ground state and it likes being home in the ground state. But when that happens, the energy has to be released out, and that is released in a photon, and it releases light. So how do we measure that? We measure that with a monochromator, which is something that measures one wavelength at a time. And a good example of that is a single beam spectrometer. So that works by having first a light source, and then the wavelengths that come off that light source are sent to a monochromator, which only observes one wavelength because it's only interested in one wavelength. And then that wavelength comes out and hits a sample of your liking, and then that wavelength passes through the sample and hits a detector. That detector tells you about that wavelength. So the sample actually absorbs some of that light. So you have this relationship because the irradiance, the light going into the sample, is different than the irradiance that comes out of the sample. That relationship is this. Because since some of the light is absorbed, there's going to be less irradiance coming out of the sample every time. And that relationship can be represented by transmittance, which states this. This is a fraction, transmittance is the fraction of original light that passes through a sample. So, absorbance and transmittance have a relationship together also. Since the sample absorbs some of the light, A, which is absorbance, equals log of final irradiance over initial irradiance. And since we know that is T, A equals negative log of T. And this tells us that when absorbance increases, the transmittance decreases. That's because when there's more absorbance, less stuff is getting through, and the light is taking away more of the wavelength. This leads us to Beer's law, or Beer-Lambert law, which is more referred to as Beer's law. And this is absorbance is directly proportional to the concentration of light absorbing species in the sample. And this is represented by the formula A equals epsilon BC, where A is absorbance, B is the path length, and C is the concentration. The path length is the distance that the wavelength travels through the sample. And the epsilon right here represents molar absorptivity, and it is a coefficient of proportionality and is wavelength dependent, and it makes the formula dimensionless, and it's a characteristic of a substance that tells how much light is absorbed at a particular wavelength. So when there's a greater epsilon, there's greater absorbance. And Beer's law only works at certain specifications, and here they are. You can read those for yourself. And then Beer's law has many limitations. First of all, in concentrated solutions, solute molecules influence each other and get too close, so this has changed properties. In a high concentration, it doesn't work because the solute becomes solvent, and then it doesn't work in a concentration-dependent equilibrium. Now, going back to measuring absorbance, there are many instruments that are used to measure absorbance. One major step for all of them, though, is that you have to record a baseline spectrum with reference solutions, either of pure solvent or a reagent blank. And this baseline has a small positive or negative absorbance, therefore it is subtracted from the absorbance of the samples to obtain true absorbance. Unless the spectrometer, if you make it the 0, then you don't have to subtract it later on in calculations. So when you create a spectrum, there are two reasons why you need to use the max absorbance. It's very important to use max absorbance. So, when you make a spectrum, this is the graph you'll get. You'll get your absorbance versus your wavelength, and you'll have these, like, different hills, I guess you could say. And this will be your maximum. The reason it is important to choose the max absorbance is because sensitivity is greatest. This point will still be, like, higher than the rest, so you'll get some detection of the analyte. Second, the curve is relatively flat, so there's going to be little variance if the monochromator drifts or the width of the transmitted band changes. Because if you look at this when you zoom in, the graph is quite flat, so if there's movement, there's not going to be much of a change. But if you choose somewhere here and there's a movement, this is a greater change in the absorbance. Okay, so now that we have a good base overview, we're going to take it to light absorption a step further. So, as we discussed before, absorbing energy equals the photon is excited, and then the photon emitted, it goes back to the ground state. So there are things called the molecular orbitals, and they describe distribution of electrons in a molecule, and electrons with different energies occupy different orbitals. So when energy increases, the electrons go to higher orbitals. And there's this thing called electron transition. Electrons from one orbital move to another orbital with accompanying increase or decrease in energy of a molecule. So the transitions that happen of electrons actually depend on the spin quantum numbers in the excited state. So, there are two possible types of transitions. The first one is a singlet transition, represented by the letter S, and the spins are opposed. That means there's one up, one down. And then the second type of transition is a triplet, which is represented by the letter T, and the spins are actually parallel, both up or both down. And T, the excited triplet state, has less energy than the excited singlet state. And the probability of transition between a triplet and a singlet state is very small. It's more probable to have a singlet to singlet transition. When energy is absorbed, we're going to look at this picture. There's a lot of possibilities. The first one is a singlet to a singlet. So energy is first absorbed up to a singlet excited state. And then that energy can relax and be more comfortable in the excited state and go down to the lowest energy of the excited state. And then that energy can be transferred to the ground singlet state. And then from there go to the actual ground state. And the transition between these two, between the S1 and the S0, is actually called an internal conversion because it's radiationless transition between states with the same spin. Another type of movement is when the energy is absorbed and it goes up to an excited state, the S1 excited state, and then it relaxes and goes down to the lowest energy in the S1 excited state, and then it moves to actually the triplet state, and there it can relax also. Moving from the singlet to the triplet is called an inner system crossing, which is radiationless transition between states with different spin quantum numbers. And those that I just talked about are radiationless, meaning that they convert energy to heat. So what happens when a photon is released? There are two types of transitions. One is called fluorescence and the other is called phosphorescence, and the umbrella term for both of these is luminescence. In fluorescence, emission of a photon during a transition between states with the same spin. So it would be a transition between a singlet state and a singlet state. So it would be the excited singlet state to the ground singlet state. And then phosphorescence is emission of a photon during transition between states with different spin. So that would be the excited triplet state to the ground singlet state. And phosphorescence has less energy and longer wavelengths because it takes longer, since it involves a change in a spin, and that makes it more improbable and harder to and less likely to occur. Fluorescence, on the other hand, has more energy and a shorter wavelength and occurs more often. Luminescence is the emission of light with an excited state of a molecule and is more sensitive than absorption. The reason for this is because luminescence has a dark background and you're observing light that comes off of a black background, and so it's striking. And absorbance is hard to measure because there's a background that's super bright. So an example of this is, say you're in a stadium and you have the lights off, and then 50,000 people would turn their lights on, like a little lighter, and then if 500 people turn it off, you're not really going to notice it. So that's absorption. But if you're in a dark stadium and 500 people light up a lighter, you're going to notice that. It's going to be more noticeable to you. There's a relationship between absorption and emission spectra. They are roughly mirror images of each other. So the energy that is absorbed is roughly the same amount of energy that is emitted. And the reason that they're not exactly the same is I'm going to show you right here. Emission comes at a lower energy than absorption. So you have your ground state, and you have your ground state. And when energy is absorbed, you go up to an excited state, right? But electronic transition is a lot faster than vibrational transitions. So when you're in the excited state, you have the energy, you have the energy of the excited state, but you have the geometry of the ground state. And you want to match the energy state that you're in with your geometry. So in order for that to happen, there's a change in the amount of energy. So now it has the excited state geometry and the excited state energy. But when the energy is released in the form of a photon, the geometry is still that of the excited state. So it has a geometry of the excited state and it has the energy of the ground state. So this is what causes the difference in absorption versus emission. Luminescence is actually observed with two monochromators, and the beginning part is similar to a single beam, but then it changes. So you first start out with your light source, and then you have wavelengths coming off that light source, and then you have a monochromator, which chooses one wavelength, and then you have your one wavelength coming off, and then you hit your sample, right? But instead of it being straight to a detector, there's a 90-degree angle in between them, and this does is minimize the intensity of scattered light reaching the detector. So then you have a bunch of wavelengths coming off your sample, and then those wavelengths hit another monochromator, and then it finally hits a detector to tell you about your wavelengths. But there's a difference between the monochromators. The first one observes excited wavelengths. The second one observes emission wavelengths. And there's two ways you can go about using a system like this. The first one is you can hold the excitation wavelength. You can keep this constant, and you can vary the emission one. And I mean by that is keep it constant is have one wavelength that you're observing, and then vary, it means like sweep it a bunch of different wavelengths. And this right here is a technique used for emission spectrum. For excitation spectrum, you do the exact opposite. You vary the excitation wavelength, and you keep constant the emission wavelength. So, emission spectrum actually looks a lot like absorption spectrum. For example, when there's greater absorbance at excitation wavelength, that means there's more molecules promoted to the excited state, and there's more emission is observed. So, the only difference is instead of there being a detection of absorbed light, it's detection of emitted light. The last thing I want to talk to you about is luminescence intensity, and that is represented by the equation I equals K POC. And I represents luminescence intensity. K is just a proportionality constant. PO we've seen before. That's the incident irradiance or the initial irradiance. And C is the analyte concentration. So the PO represents the light that is going in. And the luminescence intensity is representing the light that is coming out. And this tells us that luminescence is more sensitive because when the incident radiance increases, the luminescence intensity increases. So that means you can improve your luminescence with a brighter light source, because when you put more light in, you get more light out and you get more detection of luminescence. So I hope you liked this video. I'm sorry it went real fast and we got through a lot of information. Hopefully it was a good review for you, and thanks for watching.